Good morning, grade 11. This is Miss Teresa. This is a video guide for the standardized test practice paper for Chapter 3, Motion in 2 and 3 dimensions. I hope you try to answer the practice paper independently before watching this video. Question 1. An arrow is shot horizontally with a speed of 20 meters per second from the top of a tower 60 meters high. The time to reach the ground will be... if we're going to draw this situation, it will look like this for a while. This is, let's say, this is the tower, and the tower is 60 meters high. 60 meters. Alright, and this is your object, let's say. Then you're going to shoot it horizontally, and of course you have a V initial here, VOX. Okay, and VOX will be constant all throughout the motion if it's a horizontal projectile motion. This motion is projectile motion, specifically horizontal projectile motion. So the VOX is 20 meters per second. Okay, and then we're required to solve for the time. For horizontal projectile motion, it acts basically like free fall, so the time to solve, the formula to solve for time here is t is equal to 2 root of 2h divided by g. Okay, then substituting, we have the height, which is 60 meters, and we have g. Of course, we know g. For grade 11, we're going to use the value 9.81 meter per second squared. Okay, so 2 times the h, which is 60 meters, divided by 9.81. Then get the root for that. The t will be equal to 3.5 seconds in the nearest two significant figures. T equals 3.5 seconds, and that would be letter C. Question 2. A projectile is launched from the top of a building with an initial velocity of 30 meters per second at an angle of 60 degrees above the horizontal. The magnitude of its velocity at t equals 5 seconds after the launch is. So we're looking for the V final. Okay, so this is a projectile at an angle, but it started at a certain height above the ground. So this is your projectile. If you're going to launch projectile high above the ground, you will have a VO, initial velocity here. VO, as given in the problem, is 30. And of course, this will have X and Y components. And then this will continue, and then it will reach the ground over here. And of course, you will have a final velocity, V. Okay. And then, of course, you will have X and Y components of that V as well. So Vx is equal to the initial VOX. Vx is equal to VOX in this case. And then, of course, you will have your Vy as well. This is your VOY, initial velocity at Y. So what are the components of these VOX and VOY? What are the values, I mean? So if this is 60 degrees, using your SOHCAHTOA, we have VOY is equal to VO sine theta. So that's 30 sine theta, which is 60. So your VOY is equal to, let's just write it over here, VOY is equal to 25.981. 25.981 meters per second. And then your VOX is, of course, cosine. VO cosine theta, which is 30 cosine 60. 30 cosine 60 will be equal to VOX is equal to 15 meters per second. So you have your VOX, initial velocity along the x-axis, which is also equal to Vx. This will also be equal to 15 meters per second. But your VOY, which is 25.981, it won't be equal to the Vy, the final Vy. And then, of course, V will not be equal to the initial velocity as well, because this is launched at an angle above the ground. It's higher above the ground. Okay, so what formula are we going to use to find for Vy? We're going to use one of the equations, kinematic equations, in along the y-axis, which is Vy is equal to V initial along the y-axis minus gt. Okay, so Vy is equal to initial velocity along the y is 25.981, as we have solved over here. 25.981 minus 9.81 times time. Time is given as, where is it? Okay, 5 seconds times 5. Alright, so our Vy is equal to 23.069 meters per second. We are looking for the magnitude of the velocity at the end over this one. Okay, now we also need Vx, but Vx is equal to Vox. If it's a projectile, Vx, the velocity along the x-axis, is constant all throughout in any of the projectile launches, whether it is horizontal projectile motion or it's projectile at an angle. Vox will be equal all throughout, but Vy, Voy might change depending upon the situation. Alright, so we have Vy now as 23.069, and Vx, because it's equal to the initial velocity along the x-axis, Vx is also equal to 15 meters per second. Now what is V, the final velocity? V is equal to root of Vy squared plus Vx squared, which we can readily use. This is Pythagorean theorem, as you know, because the final part, this one is the final part, you will see that these are resultant vectors, so you are going to apply Pythagorean theorem in that. Okay, using this, Vy squared is 23.069 squared plus 15 squared, and then you get the root of that. Your V, let me just change the color so that we will distinguish. Your V will be equal to 27.51 meters per second, and using two significant figures only, you're going to get 27.5 meters per second, and your final answer will be letter D. Question 3. A ball is thrown at an angle. Question 3. A ball is thrown at an angle between 0 degrees and 90 degrees with respect to the horizontal. Its velocity and acceleration vectors are parallel to each other at a launch angle of... Okay, so this question tests your knowledge about acceleration when a projectile is launched. Now you have to remember that the only acceleration of a projectile is the downwards acceleration due to gravity. So whether, let's say this is your projectile, then you will launch it at an angle, and then it will, if it's an ideal projectile, it will follow this trajectory. So at every point, at any point of the projectile actually, the acceleration is always downwards. At any angle, the acceleration is always downwards. There is no vertical, there is always a vertical acceleration, and it's always downwards, and it's always 9.81 meters per second squared. There is no horizontal acceleration. The horizontal acceleration here, AX, is always equal to 0, but AY, the acceleration along the y-axis, is always equal to 9.81 meters per second squared, and it's always downwards. Now at this point, okay, so this is the starting position. The acceleration here will be 0, But then as you launch it, the acceleration will start pointing downwards until it's the end. Okay, but then here at the highest point, let's say this is your H max, at your highest point, the vertical acceleration here is Vx, like this, Vx, and the acceleration is downwards, Ay, and they are perpendicular to each other. So at this point of your projectile, the acceleration is, and the vertical acceleration, the acceleration is perpendicular to the Vx. Okay, now how about at which angle will the velocity and the acceleration be parallel to each other? At which angle is that? We will not be able to observe it if the angle is between, let's say, let's say it's 60 or 30 and so on. But then if we are going to launch it at an angle, let's say this is your projectile over here, this is the ground, then you're going to launch it at 90 degrees. Okay, the acceleration here will be Vy, upwards, and the acceleration will be downwards as it is moving up. So in this case, if we are going to extend the lines like this, downwards and upwards, okay, they are parallel to each other. Okay, so at this angle, at 90 degrees, at this angle only will the velocity and acceleration will be parallel to each other. Therefore, the answer for this question will be 90 degrees. Question 4. During practice, two baseball outfielders throw ball to the shortstop. In both cases, the distance is 40 meters. Outfielder 1 throws the ball with an initial speed of 20 meters per second. Outfielder 2 throws the ball with an initial speed of 30 meters per second. In both cases, the balls are thrown and caught at the same height above the ground. Okay, so this situation doesn't have a question. So, you don't know what to answer. Basically, we just say that the answer cannot be decided upon the information given. And even if the question is given, let's say there's a question over here, let's say what is the range, what is the range of the ball which the outfielder 1 throws, we will not be able to answer it as well because there's no angle given. Now in projectiles, angle is given, or maybe angle is unknown and the other two velocities are given, the x and y, Vx and Vy velocities will be given, not just the initial velocity. So that will be able to solve for an angle, and then we'll be able to solve for the range. But then in this case there's no question, therefore our safest answer will be letter D. Question 5. A 50-gram ball rolls off a countertop and lands 2 meters from the base of the counter. A 100-gram ball rolls off the same countertop with the same speed. It lands blank from the base of the counter. So there are two situations over here. First one is the 50-gram ball. 50 gram. It rolls off the countertop and then it reaches, the VO is 0 initially, and then it reaches 2 meters away from the countertop. This is your range. Okay, and then there's a second situation where the same countertop, you're going to roll off a 100-gram ball this time. 100-gram ball. Now you're being asked what is the range that this will be reaching. This ball will be reaching. Will it be less than 1 meter? Is it 1 meter, 2 meters, 4 meters, and more than 4 meters? The answer here will be letter C. Okay, 2 meters as well. Why? Because the formula for the range actually is, for any range, if we have horizontal projectile motion, the range of a projectile motion, horizontal projectile motion, is equal to Vx, the velocity, times time. There's no mass in our formula, and even if you're going to roll off a ball, maybe launch it at an angle, projectile at an angle. The range formula for projectile at an angle, sorry about that, is equal to VO squared sine 2 theta divided by G. And nowhere in your formula, you cannot find anywhere in your formula M. M is the mass. So mass does not affect the range reached by a projectile. Okay? We see that none of these quantities, this one R and R, depend on mass. There is no mass in the formula. Therefore, it does not affect the range reached by the projectile. The answer is 2. Question 6. For a given initial speed of an ideal projectile, there is or are blank launch angles for which the range of the projectile is the same. Okay, so this question is basically asking, will there be a range, okay, in a projectile, will there be a range that you can calculate where you launch it at an angle and then you get the same range, if you know what I mean. Okay, so actually for a projectile, if one of the properties of a projectile, if you launch it at a 45-degree angle, if it's 45 degrees, this angle will give you the longest range. Okay, this one will give you the longest range, the highest range that you can have at any mass, okay, at any velocity. Let's say same initial velocity. If you launch it at 45 degrees, then you will get the longest range. But let's say you're going to launch it at, first you will have 30 degrees, this one, 30 degrees, you'll launch that at the same initial velocity, and then you're going to launch it as well at 60 degrees. Let's assume that this is 60 degrees. Okay, now what range will you get? For 30 degrees, maybe it will reach until here, and for 60 degrees you're going to reach the same range. Okay, this is one of the properties of launching angles of a projectile. The range of 30 degrees and the 60 degrees at the same initial velocity will be equal. Why? Because they are complementary angles. Alright, so if you launch it at, let's say, 30 degrees and 60 degrees, the range are equal. Why are they equal? Because the angles are complementary. It means that if the angles, if you add them together and they are equal to 90 degrees, their range will be equal. You can have different angles as well. You get the 25-degree angle and its complement, the other angle, let's say, being the complement of 25 degrees. I don't have my calculator right now. I cannot calculate on top of my head as well. Okay, that will give you the same range. Therefore, the answer here will be only one if the angle is 45, but otherwise two different. Okay, two different angles, if they are complementary, it will give you the same range. But 45 degrees, because it's a complement to itself, 45 plus 45 is equal to 90, you'll get the same range as well. So, but 45 degrees will give you the longest range. Alright. Question 7. A cruise ship moves southward in still water at a speed of 20 kilometers per hour, while a passenger on the deck of the ship walks towards the east at a speed of 5 kilometers per hour. The passenger's velocity with respect to Earth is... Okay, so this question is about relative motion. I hope you remember relative motion. Okay. Now, one example of relative motion is that when you are inside the bus is moving forward at 2 meters per second and you're moving backward at 2 meters per second. What is your velocity, if you remember that? problem that we have discussed in class. Now, in this case, a cruise ship is moving southward. Okay, the velocity of the ship, okay, V of the ship moving southwards is 20 kilometers per hour. And then there's a person inside the ship, cruise ship, who is walking passenger on the deck of the ship, and the passenger is walking towards the east, this way, walking towards the east. V of the passenger is equal to 5.0 kilometers per hour. Now, we're going to calculate for the velocity, the passenger's velocity with respect to Earth. Now, this is only equal to the resultant of the two velocities over here. Alright, so here is your x-axis, and then here is your y, Vy as well. Then they are equal to each other if you're going to draw that. Now this direction, the blue one, this one, is the velocity of the passenger, with respect to the Earth. Okay, that's just resultant. So if we're going to solve that, the velocity of the passenger with respect to WRT, the Earth, is just equal to the root of, okay, this is just Pythagorean theorem. If you can identify, V of the ship squared plus V of the passenger, PASS squared. Okay, then substituting the values, 20.0 squared plus 5.0 squared, then V of the passenger, velocity of the passenger with respect to the Earth, will be equal to 20.6 kilometers per hour. Okay, so this one, the blue line is 20.6. Let me just rewrite that. Wait, please. I'll just use a smaller pen so that we have space. Okay, so that blue line is equal to 20.6 kilometers per hour. So you think we're done, but in your choices you have A and B. A is 20.6, B is also 20.6, and E is also 20.6. Now the only thing that we need to solve for is the direction of the 20.6 kilometers per hour. So we can use tangent. Okay, tangent theta is equal to 20 over 5. Okay, because this is 20 and this is 5. Here, this is 5, the red line is 5. We're solving for this theta. Okay, 20.0, that one. Then theta in this case will be equal to 75.9 degrees. And then if you look at your choices, there's no 75.9 degrees, but then we have the directions east of south and south of east. What is south of east and what is east of south? Which one are we going to choose here? The answer here will be A, 20.6 east of south. Okay, because if this theta is equal to 75.9 now degrees, so this one you minus 90 minus 75.9, you will get 14.04. Is it 14.04 degrees? But this direction is east. This is east of the south direction. Therefore, your answer is letter A. Question 8. Two cannonballs are shot from different cannons at angles theta 1. Initial theta 1 is equal to 20 degrees and initial angle 2 is equal to 30 degrees respectively. Assuming ideal projectile motion, the ratio of the launching speeds VO2, initial velocity 2 and initial velocity 1, for which the two cannonballs achieve the same range is. Okay, so you're given two cannonballs. They are shot from two different ranges. Let's just draw that for a second. So this is the first cannonball, and it's shot at first 20 degrees, and the other one, the other cannonball, is shot at 30 degrees. Okay, now assuming ideal projectile motion, the ratio of the launching speeds, you're going to find for VO2 and VO1 the ratio. VO2 divided by VO1, what's the answer? Okay, and assuming that they are in ideal projectile motion, so we're looking for range of the two. What is the ratio of the range between the two? Okay, so let's just erase this and let's list the given first. Okay, it's always a good idea to list your given. So theta, initial theta 1 is equal to 20 degrees, and initial theta 2 is equal to 30 degrees. Okay, but the range of the first cannonball is equal to the range of the second cannonball, according to the problem. The formula for range is R is equal to VO squared sine 2 theta divided by G. Alright. But R1 is equal to R2. Okay, so R1 is equal to R2. Therefore, the VO1 squared sine 2 theta divided by G is equal to the VO2 squared sine 2 theta divided by G. So I just equated the formula for range 1 and range 2. If I use range 1, I will use VO1. If I will use range 2, I will use VO2. Okay, we can cancel out G and G in this case because they're equal. How about sine 2 theta and sine 2 theta? Can we cancel them out? No, because the thetas are not equal. Okay, let's just assume this is theta 1 and theta 2. Initial theta, initial. Okay, now we're going to substitute those two values of theta. So VO1 squared sine 2 times the first theta is 20, so sine 40. Sine 40 is equal to VO2 squared sine 2 times 30 is 60, sine 60. Okay, we want this ratio VO2 over VO1. So we divide both sides by VO1 squared so that we will have VO2 over VO1. We can now cancel this and this. Okay, so we have sine 40 is equal to VO2 squared over VO1 squared and sine 60. Okay, we continue here. Let's use another color. Now we have VO2 squared over VO1 squared, and then we need to isolate VO2 squared and VO1 squared in one side. Therefore, we divide both sides by sine 60, so we can cancel this. Now we have sine 40 over sine 60 is equal to VO2 squared over VO1 squared. We need VO2 and VO1 only, so we have to use the root. Okay, get the root of both sides to cancel the square and square. So now we have VO2 divided by VO1 is equal to the root of sine 40 divided by sine 60. The answer for that will be 0.862. So that ratio is letter B. That's the final answer. Question 9. The acceleration due to gravity on the moon is 1.62 meters per second squared, approximately a sixth of the value on Earth. For a given initial velocity VO and a given launch angle theta initial, the ratio of the range of an ideal projectile on the moon to the range of the same projectile on Earth, our moon by our Earth, will be approximately. Okay, so this question is similar to question 8, just that now we're going to get the ratio of the range of the projectile on the moon and the range of the projectile on Earth. Our moon divided by our Earth. Previously, the R1 is equal to R2. Now we're going to get our moon by divided by our Earth. Okay, so in this situation, they have the same launch velocities, okay, initial velocities, and same theta angles. Okay, so we know that R is equal to VO squared sine 2 theta, right? So the theta and the V are equal, but then divide by G are not equal. So we're going to get the ratio between our moon and our Earth divided by our Earth. Okay, so the formula for the R on the moon will be equal to VO squared sine 2 theta divided by the G on the moon is 1.62 over, okay, over the the R on Earth, VO squared sine 2 theta. The theta and V are equal, so I'm not changing them, and the G on Earth is 9.81. So this VO squared sine theta and VO squared sine theta, because they are equal, we can cancel them. Therefore, we can rewrite this as 1 over 1.62 over 1 over 9.81. Okay, simplifying that, this is a complex fraction. We can simplify by 1 over 1.62 multiplied to 9.81, get the reciprocal over 1. So basically you're dividing them. If you divide, you will get 6.05. In our choices, there's no 6.05, but if you round it off to the first one significant figure, you'll get 6. So this is your answer. Question 10. A baseball is launched from the bat at an angle of 30 degrees with respect to the positive x-axis and with an initial speed of 40 meters per second, and it's caught at the same height from which it was hit. Maybe you will have a problem understanding that. It's caught at the same height from which it was hit. It just means that you start this projectile at this height, and then it will go to its trajectory, and then it will still be at the same height at the end of the projectile motion. That's it. Assuming ideal projectile motion, the positive y-axis is upward, the velocity of the ball when it is caught is, alright, so the initial velocity in here is 40 meters per second. So this one, VO, is equal to 40 meters per second. Now, since it was caught at the same height at the end, it will still be equal to 40 meters per second. But now it is negative because it's now downwards. Here it is upwards, so it is positive at the initial phase. Okay, so we have VOX over here. VOX initial is also equal to the final. It's always equal to each other. VOX is always equal to VOY, VX, sorry, that's VX final velocity along the x-axis of any projectile. Okay, even if it's a horizontal projectile motion or projectile at an angle, it's always equal. But VOY will change depending upon the situation. VOY and VY will change according to the situation. And how about this one? Of course, you have a VOY over here, VOY, and you will be able to solve for VOY and VOX using SOHCAHTOA. Okay, and in here it's also equal since they are of the same height when it was hit and it was caught, same height. So VY final is equal to VOY, but just in the negative direction. Okay, so VOY is equal to negative, not equal, they're not equal, just the magnitudes are equal. Let's say VOY is 5 meters per second. The VY is also 5 meters per second, but in the negative direction. Alright, so let's not write that, but they're equal. Alright, magnitudes are equal. Now, how to solve for VOY? This one, VOY. And VOX, VOY is equal to V initial sine theta. Okay, your theta over here is 30 degrees. And VO is 40. So 40 sine 30. So your VOY is equal to 20 meters per second positive. So your VY, the final one over here, will just be the negative of that, negative 20 meters per second. For VOX though, VOX is equal to VO cosine theta. VO is 40, cosine theta is 30. So your VOX is equal to 34.64 meters per second positive, and it's still equal to VX. This one still positive. Okay, because it's going to the east in this case, but VY will change its direction, therefore it's negative 20. Now, what is the velocity of the ball when it's caught? So we have these along the x-axis and this along the y-axis. So if we are going to use the vector form of this, it will be 34.64x minus 20.00y, and both of them will be meters per second. If you want to solve for the velocity, of course you can use the Pythagorean theorem, but in our choices it's not given as that, it's given as vectors. Okay, vector points, so you're going to just use this you can write it in this form only. Okay, so the answer here will be letter C. Question 11. In ideal projectile motion, the velocity and acceleration of the projectile at its maximum height are respectively. Okay, so first we're going to analyze the vectors of projectiles launched at an angle. because this is what the question is all about. Let's say, for example, that your projectile is launched at an angle. It will reach its maximum height over here approximately, and then it will reach the same level over here approximately. Okay, so let's put some other objects over here, same object but at different positions. All right, so let's analyze the projectile first. We're going to analyze the acceleration of this. The only acceleration again of a projectile is the downwards acceleration due to gravity. So at this point, this is downwards g, this is downwards g, this is downwards g, and this is downwards g, and they are all equal to each other. It's constant. Okay, so you should have your vectors of the same size. The red arrows should have the same size approximately, because I didn't use my ruler to draw that. Okay, next, is there a horizontal acceleration? For projectiles, there is no horizontal acceleration. Okay, there's no horizontal acceleration for projectiles. Now, how about horizontal velocity? Horizontal velocity is constant. Okay, so let's say, for example, you launch this at an angle. Okay, and this is your VO. Okay, your VOX is constant. At this point, it's equal to VOX. At this point, it's equal to VOX. This point equal to VOX, and this point equal to VOX. Okay? Next, the vertical velocity changes direction and magnitude during the trajectory. Okay, what does it mean? Let's use green this time for the Vy. Okay, so Vy at the start, okay, will be the highest. And then as it is going up, it's becoming smaller and smaller. At the highest point, Vy is equal to 0. Okay? And then as it goes down again, and it'll be down over here, Vy, and then it'll be Vy again over here, going down, Vy. Okay? It's greatest at initial and greatest at the final as well. And as it is going up, it's becoming smaller and smaller, because the g is downwards, it's opposite its direction, therefore it will affect it. It will make the value of it smaller. All right, so those are the things that we need to know about projectile. Now the question is, what is the velocity and acceleration of the projectile at its maximum height? This one. Okay, respectively, what? Negative, right? The velocity is negative, and acceleration, velocity. First, we have to talk about the velocity. It should be, which velocity are they talking about? Okay, I don't know which velocity. 0. Okay, velocity is 0 over here, but vertical velocity is not 0. Right? And then, this is question number 11, right? The vertical velocity, Vy is 0, but the vertical velocity Vx is horizontal. Yes, horizontal. And then, the acceleration is downward. Okay, so which answer is that? It's letter A. Horizontal velocity and downward acceleration. Question 12. In ideal projectile motion, when the positive y-axis is chosen to be vertically upward, the y component of the acceleration of the object during the ascending part of the motion and the y component of the acceleration during the descending part of the motion are respectively. Okay, so we just discussed this in the previous slide. It's just talking about acceleration. What's the direction of the acceleration? This is the ascending part. Ascending meaning going up. Ascending. And this is the descending part. It means it's going down, the descending part of the projectile motion. Okay, so in the ascending part, what's the direction of the acceleration? It's downward. Okay, so it's negative. Now, how about in the descending part of the acceleration? It's also downward. So it's also negative. At this part, it's downward. At all parts of the projectile motion, the acceleration is negative. Therefore, the answer for number 12 will be letter D, negative, negative. Question 13. In ideal projectile motion, when the positive y-axis is chosen to be vertically upward, okay, the y component of the velocity, Vy, okay, of the object during the ascending part of the motion, and the y component of the velocity, again Vy, during the descending part of the motion are respectively. Okay, they're asking you what's the sign of Vy on the ascending part going up and going down of the projectile. So again, we are going to discuss, we've already discussed it in slide number, I don't know which slide is that, but then we did. Okay, so this is the ascending part, the going up portion of the projectile ascending, and then this is the descending part. Okay, what is the direction of Vy on the ascending part and the descending part? In this part, it's going up, and this part, it's going down, Vy. Okay, Vy over here, Vy. At the first part, of course, is the largest Vy. Here, Vy over here is, okay, there's no Vy over here. Vy is equal to 0, but Vx is constant, and then Vy over here is going down as well. So in the ascending part, Vy is positive, and in the descending part, Vy is negative. Therefore, the answer will be positive, negative, letter A. Question 14. A projectile is launched from a height YO is equal to 0. So it means it started from the ground and it will end up on the ground as well. For a given launch angle, if the launch speed is doubled, what will happen to the range and the maximum height of the projectile? So we are talking about the range. Okay, let me just use another color so they can see it. We're looking for the range and the height if the launch speed is doubled. First, we're going to list the formula for R. Okay, R, we know that R is equal to VO squared sine 2 theta divided by G. Okay, but if VO, it says in the problem, is doubled, it means that you're going to multiply it to 2, doubled. What will happen to the range? Okay, so what will happen to the range if VO is doubled? So R is equal to, you're going to double VO, so 2 VO squared sine 2 theta over G. Okay, so simplifying that, R now will be equal to 2 squared is 4 VO squared sine 2 theta over G. Okay, so R is, in this case, it's multiplied to 4 if we double the V. So this means it has quadrupled. It's multiplied to 4, quadrupled. How about the H? Okay, what will happen to H? So first we're going to list the formula for H max in this case. H max, the maximum height H, is equal to VO squared sine 2 theta, no, sine squared theta, not 2 theta, sine squared theta, sine squared theta divided by 2g. Okay, if VO is doubled, what will happen to H? Okay, so we'll do the same thing. Now H is equal to, you double VO, okay, 2VO squared sine squared theta divided by 2g. Okay, so it'll become H is equal to 4VO squared sine squared theta over 2g. But there's 2 over there on the what's this, denominator, so 4 and 2 will cancel out. It will become 2 over here. So finally we can rewrite the H is equal to 2VO squared sine squared theta over g. Okay, so in this case 2g, it has doubled, but should we cancel that? No, actually we don't need to cancel that, because that is the exact formula already. Okay, so this will be 4VO squared over 2g. So this is the formula, original formula. What did we do to the original formula? We multiplied it to 4. So it also has quadrupled. So both of them have quadrupled. So what's the answer over here? Quadruple and quadruple, so letter B. Question 15. A projectile is launched twice from a height YO is equal to 0 at the given launch speed VO. The first launch angle is 30 degrees and the second launch angle is 60 degrees. What can you say about the range of the projectile in these two cases? So I have discussed this already in one of the slides. It says that if you're going to launch a projectile at first at 30 degrees, okay, then it will reach this approximate range R. Okay, and then if you're going to launch it at 60 degrees, let's say this is 60 degrees, this is 60 degrees, it will also reach this same range. If you want to verify this, you can go to the virtual lab that I've given you about projectiles, the one that we used for our project, and try to launch the projectile at the same initial velocity, but you launch it at 60 and 30, you'll get the same range. Or any angle that are complementary to each other. It means that the angles, if you add angle 1 plus angle 2, it's equal to 90 degrees. Any angle which are complementary, meaning they add up to 90, the range will be equal as long as the initial velocity is the same. Alright, so the answer for this is letter A. R is the same in both cases. So that's it for the projectile video. I hope that it has answered some of your doubts. If you have more doubts, you just send me a message and then we'll talk to each other, maybe at an extra class. Good luck to your exams. Let me see if I can make another video for the other chapters, but this is the chapter that you're having difficulty with. So good luck.